Hello everybody, today we will be talking about calculus for chain rule. So last thing we talked about was the definition of derivative, actually not the definition of derivative, it was the how to find the derivative of trig function. So that was, I think, like section 3.3 or something like that. So today we'll be talking about something called the chain rule for calculus, and what that means is the following. Here you can see I set up an example where I want to take the derivative of sine of 2x. So meaning, how do you take a derivative of a function that has a inner function, or basically a function that is a composite function? The question is, well, what is the derivative of this guy over here? One might think that, okay, well, the derivative has something to do with cosine, but the question is, well, what is that 2x inside? Is it going to change my answer in any way whatsoever? Is the answer just plain old cosine of 2x? Unfortunately, it's not going to be that simple. So let's go ahead and take a look at this graphically so you can see what I mean. So here we will go to Desmos, and we're going to go ahead and graph both of the scenarios. You can see that I have two functions right here. In the red, number one, that is supposed to be what we just said, the sine of 2x. That's the equation right there. You can see that's a smaller function right there. And the derivative of sine of 2x, it's going to be, in this case, the blue function. So Desmos is kind of nice that it can actually graph out what the derivative actually looks like. And now in comparison to what we were saying earlier, you'll notice that, yes, one part is that looks like it's going to be a cosine function because the period is about the same thing, but you'll notice that one big difference is that the amplitude is actually different. In fact, the amplitude is going to be 2 with the derivative function. So if I'm looking at it carefully, then it looks like the derivative is going to be cosine of 2x all multiplied by 2. And let me just go ahead and kind of like do this down here so you can kind of see it. So if I take, like, say 2 multiplied by the cosine of 2x, you can see now that is literally going to be the same graph right there. So in conclusion, that is going to be our derivative then. So now if I go back here, let me just go ahead and fill in the void right here. The derivative turns out to be 2 multiplied by the cosine of 2x then. So the question is, well, where's this 2 coming from, and how do we actually approach it, and how do we actually get it then? So first, what I'm going to do is I'm going to go ahead and give you what the chain rule says about what the derivative is. And then afterwards, we're going to go ahead and derive it. So here's how it works then. If you have to take the derivative of a composite function, we'll call it f of g of x. It turns out that according to this chain rule, the derivative is going to be the derivative of the outside function, and then you still have the composite in the inside, basically the cosine of 2x that we just saw right there. But on top of that, you're now going to multiply by the derivative of the inside function. And so you'll note that in our previous example, the inner function, which is supposed to be 2x, that is basically what we're going to be multiplying by its derivative. So that's where the 2 is actually coming from. So to give you some numerical examples, so then that way we can get a better idea. So for example, if I say, hey, take the derivative of tangent of 2x, first the derivative of tangent, the outer function, we say that that's going to be secant squared, and then it's still going to be same inside argument of 2x. But now we're going to multiply by then the derivative of the inner function, which is 2x. So then the answer is going to be 2 multiplied by secant squared of 2x then. For the second one, same idea. First, we're going to, if I want to solve for what is the derivative of e to the sine of x, then the answer is that it's going to be e to the sine of x, which is its derivative, right? Then we're going to multiply by the inner function's derivative. So the inner function being sine of x. So if it helps, what I usually like to do is underline or underscore what is the inner function, so we know that the chain rule is being activated. The derivative of sine is going to be cosine, so my final answer is e to the sine of x multiplied by the cosine of x. And then later on, we can also find out what is the derivative of 7 plus e to the tan x raised to the 5th power. We're going to get back to this one actually because that one's a little bit more difficult, so it requires multiple chain rules. So we'll come back to it in just a few. But for right now, what I want to do is go ahead and derive the chain rule for you so you can see where that is actually coming from. So here we can say that given that y is equal to f of g of x, I want to prove that y prime is equal to what we just said, the f prime of g of x multiplied by g prime of x. So the way we're going to prove this is by using the formal definition of derivative, but not the one that we normally use with the limit as h approaches towards 0. This formal definition of derivative is the one that we rarely see at all. If you want, I can go ahead and write on the side right here. It says the following. If I want to solve for the derivative at the value of x is equal to a, the derivative is supposed to be the limit as x approaches towards a of f of x minus f of a, all divided by x minus a. And I'm pretty sure that most of you guys have seen that back in chapter 2 or a while back when we first introduced the limits. But we don't really use this as our formal definition of derivative. We use it once in a while just to kind of help us out with the algebra, and that's what's happening in this case. So this is basically where I came up with this part right here. So again, we're going to go ahead and say that y is going to be f of g of x. So according to our definition of derivative, this one right here, then this is what we're going to get as a result. The limit as x approaches towards a of f of g of x minus f of g of a, all divided by x minus a. Now for this guy right here, what we're going to do is we're going to go ahead and sneak in something so you can see where it's going to go to. The limit as x approaches towards a of f of g of x, so I'm just going to rewrite, minus f of g of a, rewrite once again. And this time, now this is the part that's going to be the trick to it. So I'm going to go ahead and create two fractions. One is going to be numerator right there, and then the other one is going to be denominator. It's going to be right here. And what I'm going to do is I'm going to introduce a part that is going to allow us to see where it goes to. That part is going to say g of x minus g of a, multiply that to both top and bottom. G of x minus g of a, multiply that to both top and bottom. Okay, so this now is going to be our kind of leap of faith. If we have the limit for both of these guys, we can hopefully see that this now we can break it into two limit problems. The second part, I think that's a little bit easier for you to see. This guy right here, what I just circled, that is really saying the derivative of g at a. Okay, that is just using, again, our formal definition. Now, the first part, if you can kind of see it, it's a little bit tricky. That is supposed to be the derivative, right? Because it's still the formal definition of f, and then it's going to be g of x going to be multiplied inward like this. Okay, so what I did was I took my formal definition and I split into two parts. So then that way you can see that one fraction is going to be a definition of derivative, but as a composite function. But whereas the second part is going to be, again, the formal definition of derivative for g of x then. So that's where the whole derivation actually comes in. So in essence, this one's actually a pretty short derivation, but it's pretty hard to see from this part to this part. So you might want to pause the video and, take a look at it, or let that kind of sink in a little bit, and hopefully it'll work out. Nonetheless, let's go ahead and try to look at some of these examples with the chain rule so you can see how it's applied. So first, we're going to go ahead and take the derivative of sine of x raised to a power, or sine of 8x. So to be able to see what the chain rule is doing, or when is it that you actually have a chain rule, let me rewrite this then. What I really want to do here is I want to take the derivative of sine of x, the whole thing raised to the 8th power. And right there, you can now see that you have a composite function, meaning a function within a function, and that's where the chain rule actually comes in. So again, we're going to go ahead and underline the inner function so you can kind of like, see the chain rule. And what people usually do is that they'll say that the inner function is going to be, we'll call it u for the time being. So we'll just say u is equal to sine of x. So therefore, du, its derivative, because we're going to need that, is supposed to be cosine of x then. Now, according to the chain rule, what we're going to do is we're going to take the derivative of the outer function. So here, let me just kind of write it using a u substitution of what we just did right there. So the derivative of u to the 8th power, because remember we said u is equal to sine of x. U to the 8, its derivative is just going to be 8 multiplied by u raised to the 7th power. Now, that's normally how you would take the derivative according to the power rule. But keep in mind, again, we have an inner function. So that means that's where the chain rule comes in. Remember, chain rule says that if you have f of g of x, right, its derivative is supposed to be the derivative of the outside function and then multiplied by the derivative of the inside function. So what that means is I need to take what I have, the 8 times u to the 7th, and multiply by the derivative of u. Okay, so that's going to be kind of like my g prime part. So putting it all together, 8 multiplied by u gets replaced back by sine, so that's going to be sine to the 7th power of x, right? And then multiply by du, which we saw for earlier, that's going to be the cosine of x right there. So you can see how the cosine of x is supposed to be the inner function's derivative. And let me actually kind of rewrite this part right here so you can kind of see what I mean by that. First, I'm going to rewrite this so that it's in a better format, and then I'm going to go ahead and change it back afterwards. So this is going to be sine of x raised to the 7th power. So now you can see that the cosine, right, that's the derivative of sine. And that's where the chain rule is actually kicked in. And now we can go ahead and clean this up and write it into a better format. 8 times the sine of sine to the 7th power of x multiplied by the cosine of x. Is there one form over the other? Not necessarily, but you should be able to recognize both of them. Okay, let's go ahead and look at the second part over here. This time I want to take the derivative of e to the t times sine of a to the t, sine of a times t. Now, the inside function is supposed to be a times t, and you'll notice that you have e to the t times the sine, so that means that we actually have a product rule that we have to look after also. So again, we'll just go ahead and write on the side. So f is going to be my first function, that's e to the t. And then g, that's my other function, that's sine of a to the t, a times t. So f prime, its derivative is just itself, so that part is not a problem. G prime, the derivative of sine of at. Now, remember, you're taking the derivative with respect to, oh, actually, I kind of messed up there. It's supposed to say d dt, so I gotta kind of make that quick minor adjustment over here. So let me just change it to make sure that it makes sense of what we're doing. Sorry, that's always my fault in that part. Okay, so back to what I was saying. When I take the derivative of g, it's with respect to t. So that means that a is basically not considered a variable, meaning that it's kind of like saying, look at it as a constant. Okay, remember, t is going to be our variable. A is not our variable in this case, where if I'm taking a derivative of d dt. So what that means is the derivative is going to be cosine of a times t, because cosine is the derivative of sine, multiplied by the derivative of at, which is supposed to be then a then. Okay, so remember earlier we were saying what's the derivative of sine of 2t? Well, the derivative was cosine of 2t, right, multiplied by 2. So that case, that's where the a is supposed to be coming from, because that's supposed to be the 2 then. So going back to what I wanted to solve for originally, right? Let's go ahead and fill everything in. So the derivative, using the product rule, right? Cross multiplication, as we did before. It's going to be e to the t multiplied by a multiplied by the cosine of at. And then we have plus, let's see, sine of at multiplied by e to the t then. Okay, and just to again help out a little bit, I'll go ahead and write that kind of like on the top so you can see where everything is coming from. So this part is going to be f, this part is going to be g prime, and then this part is going to be g, and then this part is going to be f prime. So that's basically piece per piece. And again, just like we say before, whenever you solve for the derivative, try to factor it, so then that way we can use it for a little bit later on. So my final form, I would probably take the e to the t that they both have in common and factor it out. So my final answer is going to be e to the t multiplied by a cosine of at, and then plus sine of at. So that will be my final answer then. Okay. Now going to the problem that we did earlier, or the one that I kind of set up but didn't solve for earlier. Here I want to take the derivative of 7 plus e to the tangent of x and raised to the 5th power. Now, to help you see why this one is a little bit more difficult, what I'll do is I'm going to go ahead and underline my inner functions. The first inner function I'm seeing is 7 plus e to the tangent of x. And the second inner function that I'm seeing is tangent of x inside the e. So what that means is I need to carry out this chain rule twice. So again, to kind of help you see it using a kind of like a substitution, here's what it will look like then. So here we're going to go ahead and write u is equal to 7 plus e to the tangent of x, right? So du, the inside, the derivative of the inner function, is supposed to be 0 because that's the derivative of 7, plus the derivative of e to the tangent of x. So I need to take the derivative of that thing right there. And let me get rid of that small little dot right there. So the question is then, well, how do you take the derivative of that thing? Well, that is going to be e to the tangent of x, because remember, that is the derivative just itself, multiplied by, the chain rule says I need to multiply by the derivative of the inner function, which is the tangent of x. So then the answer is supposed to be e to the tangent of x multiplied by the secant squared of x. Okay. Now, let me put it all together so you can maybe see a little bit better, because if I break it down piece by piece, it might be a little bit too hard to see. So here's the final answer supposedly in this case then. First, the outermost function is supposed to be something to the fifth power. So if I have something to the fifth power, its derivative is supposed to say 5 multiplied by 7 plus e to the tangent of x and then raised to the fourth. So that's the outermost function's derivative. Next, I'm going to multiply by the inner function's derivative, which is supposed to be e to the tangent of x, okay? Because that's supposed to be that inner part. And then we're going to multiply by its inner function's derivative. So that's going to be multiplied by secant squared of x. Okay, so the question that I always ask myself is that, okay, when you take the derivative of the inner function, be it a chain rule, is there still going to be more inner function? If the answer is yes, then you have to keep doing the chain rule. And you have to keep going so on and so on and so on until you finish every single one of them. Okay, here, maybe I can do one more example on the side just so you can kind of see how this actually works out one more time. So let's say this time I have a sine of, I don't know, how about, let's say, sine of cosine of x squared. Okay, so this is just kind of like something I'm just going to make up on the side. The derivative, so here's what I'm going to do first. I'm going to go ahead again, underline the inner functions. So here's one part, and then here's the second part. So that tells me that I need to do the chain rule twice. So the first part, my derivative of the outside function is going to be cosine, right? And it's going to be the cosine of just rewrite what we have inside. Okay, so cosine of the cosine x squared. Multiply by the first part, we're going to multiply by the derivative of the inner function because of the chain rule. So that's going to be equal to the negative sine of x squared, right? Because remember, that's going to be the derivative of what I underlined there. And then that now is going to be multiplied by 2x because there's still an inner function within, which is x squared, and its derivative is 2x then. So this whole thing would then be the derivative of this thing that I just kind of came up with on the side then. Okay. Now, I will go ahead and do a couple more with this one. And normally this derivative of ln of x, the derivation of it, comes in a later chapter. But I found out that this actually could be solved for right now. So this is something that we can actually take advantage of. So what I want to do is I want to take the, I want to derive what is the derivative of ln of x then, which is supposed to be the inverse function of e to the x. And again, you'll see it in the future section in a little bit. What we'll do first is we're going to go ahead and say e to the ln of x is equal to x. And that is just something that we had a while back when we first learned logarithm, that if you have e and ln next to each other, it cancels out to be just what's in the inside argument of ln of x then. Okay, so that statement is definitely true because e and ln, they cancel each other out. What we'll do is we're going to go ahead and say, I'm going to go ahead and take the derivative of both sides. So the derivative of the left, right? So the derivative of e to the ln of x is then equal to the derivative of x then. So, just operation both sides, take the derivative of both sides. Now, on the right-hand side, that's easy enough. The derivative of d dx, the derivative of x is just equal to 1. The derivative of the left-hand side. Now, this is where the chain rule comes in, because if you notice again, we have an inner function right there. So what we'll do is we'll just go ahead and write that out then. So first, the derivative of the function as is, the outer part is going to be e to the ln of x, right? That's the derivative of e to anything. Normally, it's just e to the anything. Then you're, according to the chain rule, says multiply by the derivative of the inner function. Okay, the derivative of the inner function is ln of x, and that's what we don't know, and that's what we're going to keep on the side. Okay, so far so good, hopefully. E to the ln of x, remember we said that that's the same thing as just plain old x from the very beginning. Multiply by the derivative of ln of x, which we don't know and we want to solve for, so we're going to leave that alone. So now if we divide both sides by x, then that means that the derivative of ln of x, what we're trying to solve for, is supposed to be 1 over x then. And now that's something that we can actually use for a lot of these things that we're going to see within the next few sections. Okay, so here I want to take the derivative of ln of cosine of 3x, and let me go ahead and make that same change because I don't want to make that mistake with mixing x and a t. So let's see here. Let me go ahead and make that into an x over here. Okay. So first ask yourself again, how many inner functions are there? Because that will determine how many times we do the chain rule. If you say 2, then you are correct because you have supposedly cosine, right? That's one inner function. And then you have 3x, that's another inner function. So that means that we're going to have to do the chain rule twice. So the first part, I'm going to look at the outermost function, which is ln. Now, according to what we just said, the derivative of ln is supposed to be 1 over x. So the derivative of ln of cosine of 3x is going to be 1 over cosine of 3x because that is supposed to be my inside argument. Then I'm going to multiply by the derivative of the inner function, right? The derivative of the inner function. So let me kind of write that out as one piece. Derivative of cosine of 3x then. Okay, so 1 over cosine of 3x, we're just going to go ahead and leave that alone. The derivative of cosine of 3x, that is supposed to be the sine of 3x, right? Because the derivative of cosine is supposed to be sine. Actually, there's a negative right there. And then we're going to multiply that by the derivative of the inner function because that inner function is 3x right there. So you can see how what I was talking about. There's 2 chain rules because there are 2 inner functions, and hence that's why there are 2 parts you're going to multiply by. So let's go ahead and clean up everything. 1 over the cosine of 3x multiplied by the negative sine of 3x, and then we multiply by the derivative of 3x, which is equal to 3. So putting it all together, that's sine of 3x over cosine of 3x, and then that's a negative right there, and then multiply by 3. Sine over cosine, that is the same thing as tangent. So we have final answer, it will be negative 3 multiplied by the tangent of 3x then, and that is going to be our derivative. Okay. Okay, so I think that's the last one. So hopefully this will help out with the chain rule. Let me know if you need me to go into further discussion because I will definitely be more than happy to go more in depth with the chain rule. But this is basically the gist of it. Okay, thank you for watching.